Hi there, here's Alessio from Dev Experience and Spectacle at Snap. This tutorial will guide you from zero to hero for understanding how to use SnapML or machine learning on spectacles. We will go through the setup in Paperspace, how a notebook runs and trains your model, how to export your model, bring it into Lens Studio, and spatialize your application for incredible use cases. In this case, we will go through a process for training a model, detecting monitors within the glasses, and shift the spatial UI from the center of your point of view to the side when you're facing a monitor. This is a very simple lens, but showcase and demonstrate how powerful this pipeline can be when runs on spectacles. In this demo, we see that we have a monitor in front of us, and we see that we have a spatial canvas. This spatial canvas is adapting to our space. Under the hood, thanks to SnapML, our device understands that we have a monitor in front of us, and it's going to move automatically this spatial canvas in a position that we prefer. So in this first part, you need to be familiar with something like GitHub, where we find SnapML templates. These templates here are part of Snapchat app and actually allows you to track a lot of objects using machine vision. We're gonna adapt one of these templates in this exercise called multi-object detection. And for doing that, we're going to take this Python notebook and use it and import it into Paperspace. Paperspace is a service that allows you to visualize your file. For example, in this case, it's going to be a Python notebook and allows you to run it on some machines that you set up on this kernel. In this case, you see that I already set up everything. What I did here is that I cloned the GitHub repository of SnapML inside our Paperspace, and then I swap actually the Python notebook with a new version that we will provide you to get started with. So we will go through all of these steps. So let's pretend that I didn't do anything in Paperspace, so we really start from scratch together. For this exercise, the first thing we will need to set up is a Paperspace account. Paperspace account allows you to set up a project, and in this project we can choose a machine of our preference and then set up a notebook, and when we have this notebook, we can go through all of the steps of the notebook. Fortunately, SnapML gives you all of the notebooks examples you need. But for this case particularly, because this time we are building for spectacles, we provide you with a new notebook that you will need to drag and drop inside of your Paperspace. So here we will need to set up a gradient account, which is the service provided from Paperspace, and we will need to set up a template. What you will need to do is creating a new project, and then you will need to name it here. So we can say tutorial, and we will create this. And we will click on create. Now you will need to select a template, and we will go with the pretty standard one, which is PyTorch 1.12. Then here you will need to select a machine that will allow you to train your models. We stay in the GPU realm because we will need the GPU to train our models. So we pick the first one here, that is the P5000. And then auto shutdown, let's extend it to 6 hours. But if you just put 1 hour, the thing is, it could just shut down entirely on its own, and you might just be in the middle of something, and that would be not good, of course, for what we are trying to do. So we start a notebook here, and this will take a little bit of time. And here you will see that you have a terminal, and then you have something here that is starting. So this is setting up your space automatically, and so on and so on. So now we have all of these files. We set up our space on Paperspace. Okay, so the first thing we want to do here is just like open a terminal. When the terminal is open, we will need to clone this SnapML templates repository. So we're going to do here, we're going to go in here, we're going to clip it and copy it in our clipboard and clone and paste. So we're cloning all of this. We will need to wait 1 or 2 minutes. Now it's cloned, and we go back in our repository. We might need to refresh to see the changes. And if you click on the multi-object detection here, you will notice you have all of these step-by-step, basically tutorial to train your model to identify multiple objects. So now we will customize this for our use case. For doing this, we can actually use a template that we provided for you. For this tutorial, we're using Paperspace, which is a service that allows you to import your files, synchronize them, and run them on a machine remotely. But this is not the only service that does this, so you're free to use the service of your preference. We just imported our new notebook file called SnapML Monitor. And this is the notebook that we will use in this example. And we will also provide you with a lot more documentation after this tutorial. So when you click on this file, you will see a slightly variation of the multi-object detection. Why do we do this? Because we want to make a general workflow for you to get started with SnapML and really become familiar with this flow, which is relatively easy and can allow you to unlock a lot of use cases on the spectacles. So here, when you open the SnapML monitor, you will see a lot of different steps. You notice that some of them are already open. This is because I already went through all of this process, but all that you will need to do is really just rerun these processes in your machine. Make sure that your machine is running, otherwise this won't work. And if it's running, let's just take a step-by-step together and let's just do what these guidelines are pointing us to. So the first step is really understanding if we are running on the right machine. And you can just run this part here and you will notice that we're all good to go. There is no running processes found. We are on our GPU machine and everything makes sense and we are ready to go with everything else. Another thing that we will need to do here is installing some dependencies. And if you're not familiar with this kind of notebook format, just know that it is pretty much a file that allows you to visualize very clearly step-by-step things that you have to do. And every time that you go through the step, you need to run them. It's the equivalent of running code on your command line, but with a nice layout for you to understand actually what's going on. So here, the second step is running the dependency. So anytime that you run one of these steps in the notebook, you will see a lot of logs in these terminals that are connected to the step that you're running. Now in this next step, we're going to understand how to use another service called RoboFlow. RoboFlow is a place where you can find a lot of different datasets which are essential for the exercise we're going through. Here's the effort is really allowing you to fine-tune this model on every use case you want. You will see that in my RoboFlow account, I already have 2 different databases which I use as a test for this process. In this case, we will use this database, which is a monitor database. So what is a database in this case is just a collection of a lot of images where the element that we are trying to detect is being detected and noted that that is a monitor in this case. This is the way that we are saying to the model that we need to detect monitors first than anything else. That, by the way, could be something that you also make on your own. So there is all of a workflow for making dataset which are very effective on RoboFlow. This is more something that you should look up if you really want to get into that route. It's something very specific. We are not going to go through this in this tutorial. But if you go on this section, which is called RoboFlow Universe, so you're going to find a lot of different databases based on just what you look for it. So for example, here, let's say I'm looking for pool, a lot of pool database comes out. This is a way for you to speed up this workflow a lot. And instead of creating your own database, just use a database which is available. Just make sure every time, maybe look through all of the notes of the database and credit these databases that you're using, or check out if they have any licenses or things like that. You will see all of these results. And I believe the one that I choose is this one here by Energy Chaser. So this is an object detection database and gives you a little bit of metrics. And all you have to do is forking this project and creating the first version of this project. So you can fork. You will need to select your space. In this case, my space is called SnapML. Then you fork the dataset. You prepare to copy this dataset. Everything is set up for you. And when it's being forked, you will need just to answer many questions here, You can also go with just the default. We just need the data set and nothing else. We don't want to make other modification to it. We are not adding any augmentation step. And then we will need to create this. And when we create it, automatically a version number is created here. This is very important. Make sure that you remember what version number is, because you will need this version number to reference in our notebook. Okay, so let's go back in our Python notebook here. This step is going to tell you a little bit what's going to happen here. And here you will need to add a number of things for getting this data set in our notebook. You will need to pip install upgrade RobotFlow. So you're basically installing RobotFlow. And then you will need to reference your RobotFlow API key. So in this case, you can find that on your settings. You can go on your account. You can go in account settings, and then you can go in API key, and then you will find your API keys here. And then when you go back into our notebook, you will need to paste your RobotFlow API key in here. Then you will need either two entries, whatever is your project name called, and whatever is your dataset name. So we go in here again in RobotFlow and check out this. So look at this on your web search input field here. You will see the name of the database. You will see the version of the database. So this is what you will need to insert. And then if you go back in your project space, so let's go in here in my projects, you will need to go into this project space. So once you get those two names, these are part of this section of our notebook. And if we have everything set up correctly, we can start again and run this step. We will have everything else set up automatically. Do not change all of these entries because we verified, at least with our workflow, that things are working fine. Once again, we will need to wait just a little bit and see all of the logs of these steps running. The dataset finished to download, so we will find it now in our YOLO folder. If you're not familiar with something called YOLO, YOLO is a machine learning model, which means you only look once. It's a very, very popular model because it's used for real-time and not real-time object detection. You can look up more information also on Wikipedia or on GitHub. But basically, this is a neural network that allows you to identify things in space and in images. And this is at the basis of all the technical stack that we are running in this exercise. So if you go in YOLO v7, and remember sometimes to refresh the Explorer, because I noticed that sometimes if I don't refresh, I don't see the changes. So if you might think you made a mistake, no, it's not. Just refresh it once again. And you will see a new folder here called monitors, TVs, and PC monitors. This is the database that we just downloaded. My recommendation in this case is to rename this database, because if there are some symbols in the name, like parentheses, commas, and dots, and slash, I think that sometimes you might find some issues in referencing that path, at least from my experience. So to just make things more solid and easy, we're just gonna rename this, and we're just gonna call it monitors. So monitors. Now we have it here, and we're all set up for going to the next step. So if you run this, you will see that we are loading from YOLO v7 monitors 1, so everything makes sense. And now we are ready for the training process. Before to get into the training process, we will need to download something that are called pre-weights, so pre-train of the Coco dataset and our weight initialization. Because we need to train the model not from scratch, we kind of need to have a support file. So in this case, we already set it up for you. This is called YOLO v7 tiny. And we can just run this again, and we should be able to download this file. Now we're good to go. We have our dataset, we have our pre-weights, we have our YOLO 7 models, and all of our directories are synchronized, and we also renamed it to make things easier. Make sure, this is a very common issue, which I see happening a lot. Make sure that everything they reference here makes sense in terms of paths. So for example, we're approaching the training step, and we will need to reference some files. 2 files in particular. First of all, make sure that you cd, so you go into the directory of YOLO v7, which is this one here. And you will see that here we have a data YAML monitors1. Moving this data YAML outside of this folder, actually duplicating it. I'm gonna moving it out of this folder. I'm gonna rename it still to data. I moved out from the monitors folder this data.yaml file. This file is gonna give us some important references. We can also remove this part of this file. Now we made this file a little bit more legible. So we have 2 names here, which will be the label that we will be able to detect through the model detection. This number is the count of all of these names. And then we have 3 paths that leads to images for testing, training, and validation. Let's make sure to modify our file path. Otherwise, our training command won't find actually those images. Monitors1, this is monitors1, and this is monitors1. It's very important to understand all of these paths where they are tipping into, because I know that this process might be kind of overwhelming for the first time you do it. So it's better that you really know what files you're looking at and what files you're pointing to. So now we will train our YOLO basic model on the database for the monitors. So it will be very strong on detecting monitors in this case. Before to start the training process, something I just want to talk about very briefly is something called TensorBoard. The TensorBoard is a tool that you can use to see visually what's happening during the training process. This is a very nice third-party service by Google that allows you to see all of the stats of your training process. So we will press run, and also we will visualize the TensorBoard, and we will also describe some of the properties of the training model stats that you will see on your terminal, just for you to understand what's going on. You run the TensorBoard first, and then you run the training process here. We just launched our TensorBoard, and now we are ready to launch our training process. You will see here everything is set up correctly. The training process just stopped, and the reason why it stopped is because this path is not correct, because I moved out the data file, and now the data file is here. So let's just understand what's going on. So data file is here, and in our SnapML monitor, let's go again to the training process, we need to have this file, which is referenced correctly. Now let's save, and let's start running our training model. So here we will see if we enable the TensorBoard, we should see something like this. And just a little note on this, sometimes a platform like Paperspace might prevent you to start a TensorBoard because they have specific channels to go through. But if you are not seeing the TensorBoard, that's okay also, because you're getting the exact same data out of these logs that you see here in the training terminal. So let's go through some of these concepts for you just to understand what's going on very quickly under the hood. You will see something like epoch, GPU memory, box, object, class, total, labels, and image size. What you need to know really is this column named total. Total is the sum of the box, the object, and the class. This is the main training loss that you're verifying. Long story short, this number needs to go down to the lowest. So that's why when you see training, you see like a kind of a descendant curve. The epoch is basically how many passes you want to go through for your training process. In this case, we set up 200. So you will see in your terminal this kind of epoch, and then you will see a number which is 9 out of 199. So that means that we are missing 191 steps before to get things done here. So this is the moment that you can take a break and just wait until your model is being trained. We just finished to train the model. This process sometimes might take you more than one try, but we set up everything for you and should not face any issue. One thing I want to bring up is that if you will take this sample and then try to adapt it to your personal use case, you might face some difficulties if your database is not high quality. So in this case, make sure always that you choose database of high quality, a lot of images, and there is very good annotation on the objects that you want to detect. Also, since we're going to take a look at these things with our glasses, if you want to also think about a relationship between the point of view of the glasses and the object that you want to detect, that's also a plus within your database. Two other steps for trying our model are the following here. So if you run this step, what you will get basically, you will try to detect monitors on a set of images that will act as a test. So the output that you will see here will be all of the processing of your images that are saved in this folder. Now in the next process, in the next step, we're just gonna showcase what is being done in the previous one. So it's just really the same thing, but we're just visualizing things to understand if actually monitors have been detected or not. Now, the final part of this step is exporting the model. Exporting the model will allow us to get different files. What we will care about is the ONX format file, which we'll import in Lens Studio in our project. So let's go ahead and run the last step here, which will save different files. I want to make sure that when you run this step, you will see all of these files at the very end. And what you will need to check is this file called best.onx. So if you go on runs, and then you go on train, and you go on detection 7, and you go on weights, this is your file that you will need to download. So you right click on it and you download it. This is the file that you will need to import in Lens Studio. A final further step is to generate label mapping. So this is mostly to understand what's going on. We already knew it from the initial data.yaml file, but here, if you generate the label mapping, you will find these two mappings. So we are sure 100% that these are the objects that have been detected. So we run all of our tests on this model, and we're finally ready to step into Lens Studio. This final part of the tutorial is subdivided in 4 sections. The first one is the import and the test of our ML model. The second one is the spatialization. The third one is the smoothing, which is layers of adjustment in Lens Studio for making our application feel better to the user. And the final part is the custom logic. In this specific case, what we will do will be shifting our spatial UI toward the side when we're facing a monitor. So whenever we are facing something, we try to purposefully move this spatial UI to the side of your favorite position. So let's go through this section one by one and in depth understand what's happening here. The second section of this process, or spatialization, is a process that you need to go through for turning these 2D coordinates that you get from the ML model into 3D spatial coordinates. The scripts you should know in this case are the ML spatializer, detection visualizer, and YOLO detection processor. If this sounds a little bit weird at first, let me just give you a different comparison, simplify things just to get things started. Just imagine that we have 4 main components in this project. The first one is the eyes, so it's the camera system. It's the system that takes the frames and sends it to the model. The brain, or the object detection, is the YOLO detection processor. This takes the image, understand what this image is about, and eventually detect, in this case, a monitor. Then we have the math wizard, which is the camera model algorithm that projects these coordinates from screen space to space. So we have this kind of screen to world transformation, which is really traditional in augmented reality and virtual reality. You will find this calculation in a lot of references or projects you will work on. Then finally, we have probably the most enjoyable layer, let's call it the artist, which is the visualization of all of this information in space. And here we have endless room for improvement, right? Because you know that as the XR engineer and XR designer, you really need to take care of this transformation from 2D to 3D. When you face a 2D image, you know that this detection box is going to be flat on an image. And the monitors, if you detect 3 or 4 monitors, are all going to be on the same layer. But if you are in space, you might face the same object or different object to be a different depth. So how do we handle this kind of noise, this kind of more complex environment ML application? We need to take into account a lot of things like, is it going to be too much if we detect, for example, 10 TV monitors in once? Do we really need to detect monitors on the edge of our field of view? Do we really need to detect monitor if we are facing down or up? Do we want to showcase these boxes only vertically, or do we want to tilt it toward us? These are all just like a lot of consideration you might go through when you're building your own application. And we are giving you a workflow to go through all of these questions. In Lens Studio, we already tested our model on a 2D image, so we are sure that things are working. Now we need to go through a 3D model in space. So let's toggle this off, and let's toggle on the ML Spatializer and the UI controller. Let's also make sure that in our simulation we are tackling spectacles, and let's make sure that we are in a 3D space here. My suggestion here is to really test things on device, because it's not really the same thing when you test things in Lens Studio and on device. You saw that now with that image, the model is working correctly. And because the speed of the building process from Lens Studio to spectacles, my greatest recommendation is to test all of these on device constantly. We give you a basic framework that will spatialize your coordinate no matter what, but you want to test your own use case on the device pretty often. So now we're going to go through an overview of things that you must know navigating this project. We have this main component, which is called ML Spatializer. So this is core script you need to know to just run things and detect objects. As you can see, there are a lot of different inputs that goes into this script. The first input is the model. So it's the monitor that we got out of Paperspace and exported as an ONX. Then we have an input texture. What is this input texture about? And if you notice here, I have something called screen crop texture. Very important and very good strategy in augmented reality and also in other similar discipline is to really focus on what you need and just disregard things that you don't need. In this case, screen crop texture is a reference to this element that allows you to crop the texture. And if you notice here in this screen crop text component, I'm inputting the texture of my camera and I'm reducing, like I'm cutting out a 30% on the edges of all of this image. Why do I do this? Because when you are facing a monitor and you want to detect a monitor in front of you for this specific use case, you don't need to detect anything else on the side. So this will give you the right focus in front of you and will make sure that every noise that happens on the edges of the image will be removed. Let's go ahead and see other things. Then we have our detection prefab. Let's take a look what this looked like. So let's go in our Spatialization, prefabs, and let's double click on this prefab. How does this detection prefab looks like? So if we go in the main parent, we will see that there is a container, which is a handy utility that reference all of the objects that are part of these prefabs. And we have 4 vertices. So if you remember what I said before about the YOLO output, YOLO doesn't output 4 vertices, but it outputs enough to understand the vertices. So in this case, we are placing the vertices in the right place, and we also have a utility to scale these vertices up or down from the center based on what we think is the right visualization for our ML model. Once again, here is very important. We take a very raw output and we make it a lot better on our application layer. This is essential for user to appreciate your application and feel very comfortable in it. If you have everything that is raw and is not filtered, things might feel a little bit challenging when you are in a spatial application, because things are a lot more invasive in a way than actually 2D screens, because it's things that you are experiencing in first person. So another thing that I want to let you notice here is that we have our prefab, and the prefab has 4 points. It's very simple. Like, these are 4 scene objects that are going to create a square. But the way we're visualizing the square is not with those raw values. The way we're visualizing the square is with values that are copy and pasted from the previous one, and they have another thing that is called match transform local. This match transform local utility is something that allows you to match the first transfer, but with some modification. For example, you can modify the speed that these objects are moving. You can lerp the speed, and lerp, if you're not familiar with the terms, means linear interpolation. And you can set the velocity of this linear interpolation. This means, for example, if an object is moving constantly like this, the other one is not going to move as much as the other one because we set up some thresholds. For example, if this first object is not moving more than this speed or more than this distance, we are not going to move the other one. So it creates this kind of level of stability, which overall results in a very good experience as a user on the device. So take care of all of these things. If you're familiar with XR, you might think of all of these smoothing behavior as filters or solvers behavior, which are the behaviors that all of these elements have in space. As you notice here, we have all of our smooth vertex. So the structure of the prefab is very simple. These are the raw output. These are instead the proxy output, which are smooth. Then we have also a center, which is not detected on the 4 output, but is detected on this proxy, so will be indirectly smooth, and has a in-between script, which apply the rotation and the position of the in-between of 2 targets. So you have element A and element B. The blend of the 2 will be in the middle, and we'll get the same rotation and middle position. Then we have another surface detection here, which is something that you can find also on the asset library. So if you go on the asset library and you go on spectacles, you can find something called surface detection. What the surface detection does, surface detection allows you to detect vertical and horizontal surfaces. We are trying to reposition a spatial canvas where we are facing a monitor, and we know that the monitor is a vertical surface. We get that for free, and we know that everything that we want to visualize or we want to detect has a very strict rule, and is basically a static vertical object. So all of these rules kind of like help you to simplify and make your experience a lot better in your application. For example, if you're detecting something that is always on a desk, you might take advantage of horizontal surface. So all of these things are really built at the layer of Lens Studio, but make a lot of difference. And in this prefab, what I'm doing is actually getting the Z, that is the depth coordinates of my surface detection. So I get the Z from another thing that you can find on the asset library on spectacles, which is called World Query Model. So the World Query Model is a raycast that allows you to hit the real world surfaces. And the surface detection is something very similar, but is more focusing on detection. So quite similar technology, but one's aimed to identify flat surfaces. The other one doesn't really care, just hit whatever point in space we find. Why I'm mentioning this too? Because the ML Spatializer takes advantage of the World Query hit and tries to project things toward that direction of the frustum of the camera, and it tries to project that toward the world and understand what you have in front of you and position things in space. But the surface detection is also another way to do that, just identifying a surface. So a blend between these two might create a lot of stability for identifying, for example, an object in space. And let's talk about some more inputs that we see here in this ML Spatializer. We have this max detection count slider. This means how many detection do we want? Most of the time, you might think you want to just detect one object, because our field of view is pretty much limited if we just think about this use case particularly. We're never going to face like 4 or 5 monitors in once. And also it doesn't make sense that we might have like 1 or 2 monitors, no more than that, in front of us. And we don't want to shift our spatial canvas just too much to the right or to the left or to the top. The detection persistence is another utility that allows you to persist in that position. The object that has been detected is going to be overlapping with our square that we just showcased in the prefab and can persist there for some time. The score threshold is threshold for a score that goes from 0 to 1 or from 0 to 100, and basically the higher the score is, the more accurate our result will be in terms of detection. The issue with this is that if your score is too high, you might also end up not detecting anything from a certain distance, or you really need to be looking at something perfectly to detect it. So my suggestion is always to keep it something like 0.6 or 0.7, which is already pretty high, but not too high to non-detect anything or just being very perfectly aligned to what you're trying to detect. Then we have a UO threshold, which is if you just have one max detection, it doesn't make sense to use it, but here you have a full description that remove redundant bounding boxes if you have multiple things that might seem the same. Then we have a ray distance, that in this case is the distance we're projecting the ray that goes from the screen space coordinate to the world space coordinate that is being detected on the frustum. So we kind of get this ray, and this ray is gonna give us eventually the point of the center of the vertices of this bounding box that we are detecting. Then we have a detection color, we have our class and labels that we verified also before in our paper space, and then we have other smoothing factor. So this is really like the part of the smoothing of the script, right? We have like a lerp smoothness, meaning you want the detection movement to be faster or slower. We have the bounding box scale, so meaning if you want to rescale the bounding box from the center to the external part of the boundary of the edge. Then we have the pinhole capture that takes care of that spatialization from the camera screen space to the world space. Then we have a text that just gives us some logs, and I added it here in this starter template. Then we have a center threshold. This is actually a very important value because this excludes every detection that goes beyond that measurement outside of the center of the detected image on the screen space. Let me explain this again. So when you're detecting things, we saw with the previous diagram that things project from screen space to world space. Whenever we get a YOLO image, we have a width and a height of an image, and things are and all of these coordinates are in that specific square. This square goes from 0 to 1 in this dimension, in Y dimension, 0 to 1 in the horizontal dimension. So what happens here is that basically we're trying to filter out every object that is detected on the edges of our field of view. So from 0 to 1, we are excluding everything above 0.4. Then we have a movement threshold, which is again something that help us to smooth movements when we are moving with our head pose. So if we're moving a lot, we don't want to probably constantly detect, or if you understand that you're facing a script and things are detected there, to avoid any drags from this direction and this other direction, you want to have a movement that it's strong enough to understand that dramatically whatever is being detected is changing. So this kind of detection outputs are so different that I'm gonna update what I'm seeing. And then we have a position lock threshold, which is still related to this movement. And then we have a stable position timeout, which is basically a delay for repositioning things. Then once again, we have a callback for when the monitor is detected and when the monitor has lost detection. So you can see how much we are building on top of what we had. And right now I'm gonna show you 3 demos that shows you the transition between a first raw output to a final smooth output. Now let's go through our custom logic that we talked about previously. So our custom logic is having spatial canvas and position it based on the detected object. So we showed before that on the ML spatializer, we have 2 callback events. One is the monitor detected function for when the monitor is detected. One is the monitor loss function, when the monitor has been lost from your detection. What you see here, you see two strings which identify two different methods that I have in this other class that is called Smart Tether. The Smart Tether is a solver which is applied on the UI controller, and this, what it does, has one default offset, which is basically a placement that goes from your point of view of the camera and just like offset the object 1 meter away from you, so here 100 centimeters, and just like keeps it in that position. But then we have two more offsets. So there is the offset without the detection of the object and the offset with the detection of the object. So this, in this case, I just kept it the same. Whenever the object is not detected, it's basically the same as the default. So it's going to be in front of us at 1 meter of distance. But whenever the object is detected, I'm going to enable a different offset, which is, in this case, 50 centimeters at the top and still 1 meter away from me. So what I'm doing here, I'm just moving the spatial canvas up instead of, and this could be, you know, right or left, could be anything that you would like. We also have a look at solver, which constantly allows you to look at the camera, so meaning looking at you from this kind of spatial canvas that you created. Now we're gonna do another demo that is gonna show you a real use case with a web page that is just part of this spatial canvas, and you're just gonna let you understand the power of machine learning application. Notice that we are not connecting with any API to just recognize that in front of us we have a monitor. This is an app that can run on every spectacle glass, and you won't need to be connected to the internet. And we are recognizing objects in front of us. This is a big difference from a previous example that we showcased also using YOLO that is called remote object detection, but we didn't really fine tune it on a specific object, but it needed the Hugging Face API connection to work. This time, this one works out of the box on every device without internet. I hope you enjoyed this tutorial for the SnapML samples for spectacles. This samples is very powerful and will allow you to customize all of this pipeline for your own use cases and build incredible lenses. We will follow up with a lot of documentation that will streamline this process. And we will also release a chess example lens that will augment all of this pipeline with AI use cases and a more complex layers of utility on top of the SnapML pipeline. If you have any question, do not hesitate to reach out. We are super active in our community. You can find us on Reddit. We share samples. We share a lot of other materials. Developers like to share their work too, and we hope to see you there soon.